Hey everyone, welcome back. We're diving into some seriously cool stuff today, quantum mechanics.
That's right. We're going to unpack this timeline you sent us, unravel the mysteries.
Yeah, a journey through the biggest whoa, what moments in quantum mechanics. So where do we even begin with this?
Well, before we go full quantum, got to set the stage. Think Newton, Huygens, Young, Maxwell, big brains, right?
Right, back in the day, they're grappling with a huge E question. What is light exactly?
Yeah, like is it tiny particles, like little bullets of energy?
Or is it waves spreading out like ripples on a pond? That's trippy to think about.
And for centuries, it was a real back and forth. But then Maxwell drops his famous equations, shows light is an electromagnetic wave.
Huge moment, right? Bringing together electricity, magnetism, and light. Like one big happy family.
Exactly. Beautiful theory, but
Wow.
there were a few things it couldn't quite explain.
Okay, like what? Give me an example.
Take black body radiation. You heat something up, it glows, right? Red, then orange, then white hot. Classic physics couldn't explain those colors.
Interesting. So that's where Max Planck comes in, right?
Mhm.
1900, bam, quantum mechanics is born.
You got it. Planck basically says, hold on, what if energy isn't smooth and continuous? What if it comes in little tackets?
Like tiny little bursts.
Yeah, like a dripping faucet, not a flowing river.
Yeah.
He called these packets quanta, a total game changer.
Okay, and then Einstein uses this idea to explain the photoelectric effect, right?
Right. And he shows that light, which everyone thought was a wave, it can also act like a particle, a photon. Nobel Prize right there.
Classic Einstein. But things are about to get weirder, aren't they?
Oh, yeah. Niels Bohr, he tackles the structure of the atom with this quantum idea.
So how did he change our understanding of the atom?
He said electrons don't just orbit the nucleus randomly, they're restricted to specific energy levels, like they can only be on certain steps of a ladder.
Okay, why is that a big deal? It seems kind of specific.
It explains atomic spectra. You heat an element, it emits light, but in very specific colors. Bohr's model nailed it.
So each element has its own unique light signature, like a fingerprint.
Exactly. And it's all because of those quantized energy levels. When an electron jumps between levels, it emits a photon of a specific color.
Okay, light acts like a particle, electrons are jumping around, then Louis de Broglie comes along with a wild idea.
Oh, de Broglie. Yeah, he goes, what if everything, not just light, has this wave-particle duality?
Hold up. Everything is both a wave and a particle. My mind is melting.
I know, right? That's some deep stuff. But it paves the way for quantum theory in the 1920s. Enter Heisenberg and Schrödinger.
Heisenberg with his matrix mechanics, Schrödinger with his wave mechanics. I remember learning about those equations. Not fun.
Right. Totally different mathematical approaches, but both describing the same quantum reality.
And then Heisenberg drops his uncertainty principle. We can't know both the position and momentum of a particle with perfect accuracy.
It's like the universe is playing hide and seek. It's not our tech, it's just how it is.
Frustrating for scientists, I bet. The universe keeping its secrets.
Totally challenged the old way of thinking. Classical physics was all about certainty. Now, probability and chance take center stage.
So how do we make sense of that?
That's where the Copenhagen interpretation comes in. It says quantum systems exist in a superposition of states. It's all blurry until you measure it.
Okay, back up. Superposition. What's that mean?
It's like, imagine a spinning coin in the air. It's both heads and tails until it lands.
Yeah, I see. It's a mix of possibilities. And the act of measuring forces it to choose a state. So observation changes reality.
Kind of, yeah. It's like the observer becomes part of the experiment. It gets pretty philosophical.
Leads to all sorts of paradoxes. Like Schrodinger's cat.
Yeah.
Always a crowd pleaser.
Right. The cat's both alive and dead until you open the box. It perfectly illustrates superposition.
Mind-bending stuff. Even Einstein wasn't comfortable with it.
Yeah, even Einstein, he and his buddies came up with the EPR paradox, trying to disprove it all.
They thought there must be some hidden variables we're missing. Some way to bring back certainty.
But experiments proved Einstein wrong. And right while this debate was happening, another breakthrough comes along.
Quantum electrodynamics. QED.
Right, QED. Finally explains how light and matter interact at the quantum level. Super precise, too.
Okay, so we have superposition, the observer effect. Now we got to talk about entanglement. It's like the ultimate quantum weirdness.
Oh, yeah. Entanglement is wild. Two particles become linked. They share the same fate. even across vast distances.
So no matter how far apart they are, they're connected. Is that even possible?
It's like they're communicating instantly, faster than light. Einstein called it spooky action at a distance.
Spooky is a good word for it. So is this spooky action actually real?
Yep, it's real. John Bell, he figures out a way to test it in 1964, and boom, experiments confirm it. Entanglement is a real thing.
Okay, so we've covered a lot of ground here, from energy packets to spooky action. Where do we go from here?
Well, this is where Richard Feynman enters the scene. He envisions harnessing all this quantum weirdness to build a new type of computer.
A quantum computer. I've heard of those. It's supposed to be crazy powerful.
They are. Regular computers use bits, which are either 0 or 1. Quantum computers use qubits.
Qubits. So what's the difference? What makes them special?
Qubits can be 0, 1, OR, both at the same time, thanks to superposition. They can do calculations in a totally different way.
Okay, so they can be in multiple states at once. That's what gives them the extra power.
Exactly. They can tackle problems that would take classical computers forever to solve, like billions of years.
Wow, that's incredible. So what can we actually do with this incredible power?
So many things. We could design new drugs, create materials with crazy properties, break encryption, even simulate the universe.
Okay, so we started with scientists trying to understand light. And now we're using those same quantum principles to revolutionize everything.
Full circle, yeah. It shows how powerful human curiosity can be. And it makes you wonder, what else is out there?
What other quantum mysteries are waiting to be discovered? What other impossible technologies will we unlock? It's pretty exciting to think about.
It really is. The future of quantum mechanics is wide open.
Thanks for taking us on this journey through quantum mechanics. We'll see you next time for another deep dive.
Absolutely. It was fun.